Okay, so yesterday practice, we had one like this where you actually have to split the volumes into two pieces. So let's start. Okay, we're going to find the solid of revolution here. Okay, but when you draw the picture, okay, so let's see. You have y equals x line, and that looks like this. Then you have your x equals 6 line, which is here. Then you have your two y lines at y equals 0 and y equals 4. Okay? So this is my bounded area. The area that's bounded by all of these functions is this area right here. Okay? All of this. Now, we're rotating it around the y equals 0 or the x-axis, which is this right here. So, if I draw this, basically we're talking about this right here. So this rotates like this. And actually, I'm going to get rid of this part in here so you can see it. This point rotates to here like this. This point rotates to here, here, so it looks like this. Say this point and this point. Okay, so this is what my solid's going to look like. Okay. Now, since we're rotating it around a horizontal line, we're going to be using this equation from A to B. My radius is in terms of x squared dx. Okay? Now, here's the thing. My solid starts here and ends right here. Okay? So let's say from here to here, this is a radius, right? From here to here, this is another radius. But notice as soon as I get to here, all of a sudden my top function becomes a different function. If I look at this one here, this radius, my radius is different. It's hitting this line instead of the y equals x line. So just like we did with bounded area, if our top function changes, we have to split our integral up into two pieces. So technically, I have two equations that I'm going to be using. This one that starts at 0 and goes to 1, 2, 3, 4. So this is going to be one integral, and then I'm going to have another one from 4 to 6. Okay? So that's the way I'm going to set it up. I'm going to have this one from 0 to 4. And then this one, my top function is x, and my bottom function is the x-axis, which is 0, dx. Then I have my second integral from 4 to 6, where my top function is y equals 4, and the bottom function is the x-axis. So this problem, just like before, we have to split it into two separate integrals. Okay? And that's probably the hardest part of this one, because the integration is going to be super, super simple. Okay? Because at this point, I'm taking the integral. This is x squared. So it ends up being pi times x squared dx plus pi, the integral of 16 dx. This is from 0 to 4, and this one is from 4 to 6. Okay? And then it becomes really, really simple. So the antiderivative of x squared is pi x cubed over 3 from 0 to 4 plus, this would be 16 pi x from 4 to 6. Okay? Plug in first one, 4 cubed, so you get 64 pi over 3 minus 0 plus this one, you end up with 96 pi minus 64 pi, which gives you 64 pi over 3 plus 32 pi, which ends up being 160 pi over 3. Now, we're going to talk about those two values real quick. Okay, so when I look at this figure that I've created, if you haven't noticed yet, this one here from 0 to 4 is nothing more than a cone. And then the 4 to 6 is nothing more than a cylinder. So you technically could have, if you wanted to, just use the equation for a cone and a cylinder to find this volume. You didn't technically even have to integrate. For instance, this cylinder part from 4 to 6, the radius here is 4, and the height is 2. So the volume of a cylinder is equal to, and if my board would help out, 2 pi r squared h. So volume doesn't like what I'm doing. Volume equals 2 pi r h. What? I must have a dead zone. 2 pi r squared h. And in this case, my radius is 4. So you just plug that in and you get that 32 pi. Okay? But yeah, you can do these in other ways as well. Okay? You could have done one or then the other, but that's the way you split it up, just like we did when we did areas.